47 years ago, we launched a spacecraft the size of a small car. It is now farther from Earth than any human object in history, racing through what NASA calls interstellar space, sending back data on its 23-watt transmitter, the power of a refrigerator light bulb. We called it a departure. We told the world we had left the solar system. Here is what we did not tell you. At its current speed, Voyager 1 will not reach the true edge of our solar system for another 30,000 years. It has traveled less than 1% of the distance to the nearest star, and its instruments are shutting off, one by one, forever. The harsh truth is that we have not left. We have barely looked up from the doorstep. This is the real story of what leaving actually means. If this video sparked even one new thought about the universe, a like costs nothing but helps everything for a small team trying to reach more curious minds. In 3, 2, 1, liftoff. August 25th, 2012. A Thursday. Most people were thinking about the end of summer, about back-to-school shopping, about whatever news cycle was grinding through that particular week. At the Jet Propulsion Laboratory in Pasadena, California, a small team of scientists was staring at data coming from an object 35 years into a journey no one had ever made before. The numbers had changed. The solar particle count had dropped sharply and without reversal. The galactic cosmic ray count had surged. The plasma density had shifted in a way that matched decades of theoretical prediction. The boundary had been crossed. Voyager 1 had entered interstellar space. Let that land for a moment, because it deserves to. A machine built in the 1970s, designed for a 4-year tour of the outer planets. Running on 23 watts of electrical power, roughly equivalent to a refrigerator light bulb, that machine, spinning slowly through the dark at 38,000 miles per hour, had traveled farther from Earth than any object ever built by human hands, and had crossed into a region of space where the sun's influence ends and the galaxy truly begins. The press called it historic. Scientists called it a triumph. A probe launched by people who used slide rules had crossed into interstellar space. We had done it. We had left the solar system. Except that we had not. Not really. Not in the way the word leaving actually implies. And that gap between the story we told ourselves and the reality those same scientists understood perfectly well is where this entire documentary lives. Here is the thing that almost never gets explained clearly. When Voyager 1 crossed the heliopause, what it actually crossed was one specific boundary, defined by one specific physical phenomenon. The point where the solar wind, that continuous stream of charged particles blowing outward from the sun, finally loses the battle against the interstellar medium, pressing in from all directions. That boundary is real. It is measurable. It has a name, the heliopause, and Voyager 1 crossed it at approximately 123 astronomical units from the Sunday. 1 astronomical unit is the average distance between Earth and the Sun, approximately 93 million miles. So 123 astronomical units is a genuinely enormous distance. It takes light, traveling at 186,000 miles per second, more than 17 hours to cover it. Voyager 1's radio signals, also traveling at light speed, take more than 21 hours to reach Earth from its current position. This is far. This is legitimately, genuinely, staggeringly far by any human standard. And it is not the edge of the solar system. Not by a significant margin, not even close. To understand why, you have to understand that the solar system has multiple boundaries, and they are not the same thing, and they are not close to one another, and the distances between them are not small variations on the same theme. They are different categories of far. The first boundary is the heliopause. That is the one Voyager 1 crossed, the point where the solar wind dies. Beyond that boundary, you are traveling through what scientists call the local interstellar medium, the thin, cold, ancient plasma that fills the space between stars. Voyager 1 is there right now. Voyager 2 crossed the heliopause in November of 2018 from a different direction, and it is there, too. Two machines, both in interstellar space by the strictest plasma physics definition. So far, so good. This is the boundary that headlines celebrate, and it deserves celebration. But then there is the second boundary, and this is where the story becomes uncomfortable. The Oort Cloud, named after the Dutch astronomer Jan Oort, who proposed its existence in 1950. The Oort Cloud is a vast, roughly spherical shell of icy bodies surrounding the Sun, at distances so immense they are barely describable in the same sentence as the heliopause. The inner edge of the Oort Cloud begins at approximately 2,000 astronomical units from the Sunday. The outer edge extends to approximately 100,000 astronomical units. That outer edge is so remote that it sits nearly halfway between our Sun and the nearest star. At Voyager 1's current speed, it will take approximately 300 years to reach the inner edge of the Oort Cloud. It will take approximately 30,000 years to cross through it and emerge on the other side. 30,000 years. When Voyager 1 finally clears the Oort Cloud, the pyramids of Egypt will have been standing for roughly the same duration they have already been standing today. The entire span of recorded human civilization, every war, every empire, every invention and catastrophe and cultural revolution will have elapsed roughly 3 times over. And Voyager 1's power will have been dead for thousands of years by then. The instruments that confirmed it crossed the heliopause will be silent ruins drifting through the dark. No one will be listening. Nothing will be transmitted. It will simply be a piece of metal, moving. So, when we say we left the solar system, what we mean, with precision, is this. We sent a machine through the solar wind boundary. That machine is still inside the Sun's gravitational sphere of influence. It is still inside the orbits of the outermost comets. It has not left the system any more than a ship that has exited a harbor's breakwater has crossed an ocean. The breakwater is real. The open water beyond it is real. But the ocean is still ahead. Now here is the third boundary, and this one requires a moment. Gravity. The Sun's gravitational pull does not stop at the heliopause. It does not stop at the Oort Cloud. In principle, the Sun's gravity extends infinitely, weakening with the square of distance, but never reaching zero. For practical purposes, the limit of the Sun's gravitational dominance, the point at which a passing star's gravity or the tidal force of the galaxy itself begins to overpower the Sun's hold, sits somewhere in the outer Oort Cloud at distances of roughly 50,000 to 100,000 astronomical units. Everything inside that boundary orbits the Sunday. Every comet that has ever terrified or delighted a civilization on Earth came from inside that boundary. The Oort Cloud, in its entirety, is part of the solar system. It belongs to our star. Alpha Centauri, the nearest stellar system to our own, sits at approximately 4.2 light-years from the Sunday. 1 light-year is approximately 63,000 astronomical units. 4.2 light years is approximately 265,000 astronomical units. The outer edge of the Oort Cloud, our solar system's true frontier, sits at roughly 100,000 astronomical units. To leave the solar system and begin the journey to the nearest star, you would need to travel more than 2.5 times the distance from the Sun to the Oort Cloud's outer boundary just to reach the starting line of interstellar space. Voyager 1, at 163 astronomical units and counting, is approximately 0.06% of the way to Alpha Centauri. If the distance to Alpha Centauri was scaled to the length of a meter stick, Voyager 1 would be sitting just past the half-millimeter mark. And yet, Voyager 1 is the fastest object humanity has ever launched on a sustained trajectory away from the Sunday. It is the best we have ever done. After 47 years of travel, it has reached the half-millimeter mark on a 1-meter journey, and its power is dying. This is not a failure. It is a fact about scale, and scale is precisely what this story is about. Because the moment you absorb that number, truly absorb it, the question of leaving the solar system stops being a question about technology or funding or political will and starts being a question about the actual, physical, unyielding geometry of space. And that question has a much harder answer than most of the headlines ever suggested. Voyager 1 was launched on September 5th, 1977. At that time, Gerald Ford had just left the White House. The original Star Wars film had been in theaters for 4 months. The internet did not exist. Disco was still on the radio. The engineers who built Voyager 1 used slide rules for some calculations. The spacecraft's onboard computer had approximately 70 kilobytes of memory. The program cost roughly $800 million in 1970s currency. And despite all of that, despite everything that makes it sound like a relic of a more primitive era, Voyager 1 worked. It flew past Jupiter in 1979 and sent back the first close images of that world's churning storms and volcanic moons. It flew past Saturn in 1980 and gave humanity its first detailed look at the rings. Then it kept going and going and going. By the time it crossed the heliopause in 2012, Voyager 1's signal was so faint that it took a 70-meter dish antenna pointed precisely at the right patch of sky to hear it at all. The signal power arriving at Earth was approximately 20 billion times weaker than the power of a cell phone signal. Scientists at JPL could detect it only because they knew exactly where to look and had built instruments sensitive enough to pull that whisper out of the cosmic noise. It was, in every honest sense, a miracle of engineering and patience. 35 years of operation, billions of miles of travel, and still transmitting. In March of 2025, NASA announced that it was shutting down more instruments on both Voyager spacecraft to conserve the dwindling electrical output of their radioisotope thermoelectric generators, which lose roughly 4 watts of power each year through the natural decay of their plutonium fuel. The low-energy charged particle instrument on Voyager 1 was scheduled for shutdown in 2026. The goal is to keep at least one science instrument running on each spacecraft into the 2030s, when even that will likely become impossible. After that, only engineering data will trickle back for a few more years before that too falls below the detection threshold. And then silence. Permanent, total silence from the farthest machines humanity has ever built. By the time you finish this documentary, Voyager 1 will be a few thousand miles farther from the Sun than it was when it started. It does not stop. It does not slow meaningfully. It simply continues on a trajectory that will carry it toward the star AC plus 79, 3888 in approximately 40,000 years. Long after every instrument aboard has failed, long after the golden record it carries will have outlasted every institution that built it, a physical artifact drifting forever through a darkness it will never fully cross. There is something both magnificent and genuinely sobering about that image. Magnificent because of what it represents, proof that a species barely out of caves could reach interstellar space within a single lifetime. Sobering because of what it reveals, that interstellar space is not a destination. It is a threshold, and the threshold is only the beginning. To understand what comes next, to understand what part 2 of this story requires, you need to sit with one more number from part 1. The heliopause sits at approximately 123 astronomical units. The inner edge of the Oort Cloud begins at approximately 2,000 astronomical units. Between the boundary we crossed in 2012 and the boundary that actually defines the edge of the solar system, there is a gap 16 times wider than everything Voyager 1 has ever crossed in its entire 47-year journey. 16 times. And that inner boundary of the Oort Cloud is not the outer one. Not by a factor of 50. We have not left. We have walked into the hallway. The door to the house is still behind us, and the street has not yet begun. The Oort Cloud does not look like anything. That is the first thing to understand about it, and perhaps the most important. Every image you have ever seen of it is an artist's rendering, a diagram, a theoretical visualization produced by scientists who have never seen it directly and likely never will. No spacecraft has visited it. No telescope has photographed it. The Oort Cloud is an inference, a conclusion drawn not from direct observation, but from the behavior of the things that fall out of it periodically and come shrieking into the inner solar system as long-period comets, trailing brilliant tails across the sky that have terrified and delighted every civilization that ever looked up. And yet, the inference is extraordinarily robust. It has been refined over decades by increasingly precise orbital mechanics. It is supported by computer simulations running on machines that did not exist when Oort first proposed the structure in 1950. It is consistent with observations of dust disks around other stars. It is as well-founded as any theoretical structure in planetary science. The Oort Cloud almost certainly exists. We simply cannot see it. What we can do is read its messages, the comets it sends inward, and from those messages reconstruct the vast library from which they came. Here is how it works. Long-period comets, those with orbital periods of more than 200 years, arrive from all directions in the sky. Not preferentially from the plane of the solar system where the planets orbit, not concentrated in any particular direction, from everywhere, randomly distributed across the full sphere of directions, as if they were falling in from a roughly spherical structure surrounding the Sun in all orientations. This is the key observational signature, a flattened disk of objects, like the Kuiper belt, that begins beyond Neptune at roughly 30 astronomical units, would produce comets concentrated near the ecliptic plane. A spherical shell would produce comets arriving from all directions. The comets arrive from all directions. Therefore, a spherical shell. Therefore, the Oort Cloud. The inner portion of the Oort Cloud sometimes called the Hills Cloud, after the astronomer Jack Hills, who proposed its existence more specifically in 1981, is thought to be denser and more disk-like than the outer spherical shell, sitting roughly between 2,000 and 20,000 astronomical units from the Sunday. The outer Oort Cloud, the spherical shell, extends from roughly 20,000 to 100,000 astronomical units. In 2025, scientists using supercomputer simulations at NASA announced a surprising result. The Hills Cloud, the inner portion, may have a spiral structure, rather than the simple disk shape long assumed. This emerged not from direct observation, but from models incorporating the gravitational influence of the galactic tide, the subtle but persistent pull of the Milky Way's mass on objects in the outer solar system. It is a candidate finding. It is not yet confirmed by observation. But it is worth knowing because it hints at how dynamic and structurally complex this region actually is, far from the featureless empty sphere that textbook diagrams suggest. The galactic tide is itself a remarkable concept worth pausing on. The Milky Way is so massive that even at the enormous distances of the outer Oort Cloud, its tidal gravitational force is measurable. Just as Earth's tidal force distorts the oceans because the Moon pulls more strongly on the near side of Earth than the far side, the galaxy's tidal force gently perturbs objects in the outer Oort Cloud because the galactic center pulls slightly differently on different parts of that vast shell. Over millions of years, this tidal force nudges the orbits of Oort Cloud objects, gradually pulling some of them out of their original trajectories and sending them plunging inward toward the Sunday. This is one of the primary mechanisms by which long-period comets are delivered to the inner solar system. The galaxy itself is reaching into our solar system and rattling the cage. The outer solar system is not isolated from the galaxy. It is continuously, subtly, intimately influenced by it. Passing stars do the same thing. As the sun drifts through the galaxy over hundreds of millions of years, other stars occasionally pass close enough, within a light year or two, to exert a meaningful gravitational perturbation on the outer Oort Cloud. 70,000 years ago, a binary star system called Schultz's star passed within approximately 0.8 light-years of the Sun, well within the outer Oort Cloud, and is believed to have disturbed the orbits of many objects there. Those disturbed objects will not begin their inward fall for thousands or tens of thousands of years. The gravitational legacy of that encounter is still working its way through the cloud right now, invisibly, slowly, at scales of time that make human history look like an afternoon. In late 2025, a remarkable interstellar visitor arrived to remind us, in the most direct possible way, what a truly unbound object looks like, in contrast to the solar-bound population of the Oort Cloud. Comet 3I Atlas, confirmed as only the third known interstellar object to enter our solar system after the interstellar asteroid Oumuamua in 2017 and interstellar comet Borisov in 2019, arrived on a hyperbolic trajectory from outside the solar system, made its closest approach to the Sun on October 29, 2025, and is now heading back out, never to return. NASA, the Lucy mission, and multiple ground-based telescopes observed it extensively. It is a comet, not a spacecraft, despite wild social media speculation, as NASA confirmed at a press conference on November 19, 2025. But its trajectory is instructive. The fact that its path is unmistakably hyperbolic, that it came from outside and will leave forever, is only visible in contrast to the orbital signatures of Oort Cloud comets, which, however elongated their paths, are ultimately bound. They reach some distant aphelion and fall back. 3I. Atlas does not fall back. It belongs to no star. That distinction between bound and unbound is the entire difference between being part of a solar system and truly being in interstellar space. The Oort Cloud objects are bound. All of them, from the ones at 2,000 astronomical units in the inner Hills cloud to the ones at 100,000 astronomical units at the outer edge, are orbiting the Sunday. They are members of the solar family. They formed, in the most widely accepted models, from the same disk of material that gave rise to the planets, and were subsequently scattered outward over billions of years by gravitational interactions with the giant planets, particularly Jupiter and Saturn. When a small body in the early solar system had the misfortune of passing too close to Jupiter's enormous gravity, it might have been flung either inward to be consumed by the sun, or outward into the far reaches of what would become the Oort Cloud. Billions of these exiles populate that shell today, sleeping in the cold and dark at temperatures near absolute zero, moving so slowly in their enormous orbits that a single trip around the sun takes millions of years. To travel from the sun to the inner edge of the Oort Cloud, you would need to cover 2,000 astronomical units. Let us make that real. Neptune, the farthest planet, orbits at about 30 astronomical units. The inner Oort Cloud begins more than 66 times farther out than Neptune. The Voyager 1 probe, at 163 astronomical units as of 2025 and traveling at approximately 3.6 astronomical units per year, will reach the inner Oort Cloud in roughly 500 years. Either way, the number is so far beyond the span of any human institution that it barely matters which estimate you use. What matters is this: Voyager 1 has been traveling for nearly half a century and has not yet reached the beginning of the region that defines the solar system's gravitational boundary. And it will be dead long before it gets there. All of its instruments will have failed. All of its transmitters will have gone cold. The machine that humanity sent to the stars will cross the Oort Cloud in silence, in the dark, with no one aboard and no one listening, over a period of tens of thousands of years, before finally emerging billions of miles from the sun into a space that is unambiguously interstellar by any definition anyone has ever proposed. In the meantime, humanity has sent a new spacecraft to study the region where the solar wind ends. The Interstellar Mapping and Acceleration Probe, known as IMAP, launched on September 24, 2025, aboard a SpaceX Falcon 9 rocket from Kennedy Space Center. It is now stationed at the first Lagrange point, approximately 1 million miles from Earth toward the Sun, and it is mapping the heliosphere boundary in extraordinary detail. IMAP carries 11 scientific instruments designed to measure the composition of particles from the boundary region, the structure of the solar wind, the incoming flow of interstellar neutral atoms, and the acceleration of energetic particles near the heliopause. It is a beautiful mission. It will tell us things we do not yet know about the physics of our sun's protective bubble, but it is worth being precise about what IMAP is not. It is not a deep space probe. It is not heading toward interstellar space. It is stationed 1 million miles from Earth, which is roughly 1/100th of one astronomical unit, and it is studying the heliosphere from that fixed vantage point, the way a weather satellite studies Earth's atmosphere from orbit rather than flying through it. IMAP and Voyager 1 represent two entirely different approaches to understanding the solar system's boundary. one by immersion, pushing through and transmitting from inside, the other by remote sensing, measuring the signatures of distant processes from close to home. Both are valuable, but only one of them is leaving, and even that one has not left in the fullest sense of the word. The Oort Cloud will not yield easily to human curiosity. The obstacles to studying it directly, with a dedicated probe that actually enters the region and transmits back data, are formidable even by the standards of outer solar system exploration. NASA's Interstellar Probe Concept Study, developed by the Johns Hopkins Applied Physics Laboratory and targeting a baseline launch between 2036 and 2041, proposes a mission to reach 250 astronomical units in approximately 50 years using the Space Launch System block, 2 rocket, a Jupiter gravity assist, and advanced radioisotope power systems. 250 astronomical units would place it well past any previous spacecraft, but 250 astronomical units is still only 1/8 of the distance to the inner Oort Cloud. It would be the deepest humanity has ever reached into its own solar system by a significant margin, and it would still be an enormous distance short of the true boundary. The Oort Cloud exists at a scale that defeats conventional mission planning, not because we lack the will or the funding, but because the physics of rocket propulsion and the speed of light combine to make the distances involved almost intractable with any technology currently available or projected for the near future. A probe traveling at 5 times Voyager 1's speed, which would require a fundamentally different propulsion system than anything yet flown, would still need centuries to reach the outer Oort Cloud. A round-trip communication, with signals traveling at the speed of light, would involve delays of months each way, even at the inner edge. At the outer edge, a signal takes approximately 19 months to travel from a probe to Earth. You would send a command and wait more than 3 years for a reply confirming it was received. The Oort Cloud is not merely distant in space. It is distant in time, in communication, in the rhythm of any science mission that expects to be run by human beings on human schedules. And yet the Oort Cloud is our solar system. It is ours. Those trillions of icy bodies sleeping in their vast orbits, perturbed by passing stars and the tidal breathing of the galaxy, falling occasionally inward to become the brilliant comets that have marked every human calendar system ever devised. They all belong to the Sunday. They orbit it. They formed from the same cloud of gas and dust that formed the Earth. In a very real sense, every long-period comet that has ever crossed the inner solar system was a visitor from the edge of our own neighborhood, a message from the outer reaches of our own home. This is the realization that makes Part 3 so necessary. If the solar system's true boundary extends nearly halfway to the nearest star, and if we have no powered spacecraft anywhere near that boundary and no realistic prospect of reaching it in any human lifetime, then the question of leaving the solar system forces a confrontation not just with distance, but with energy, with physics, with the raw mechanics of what it actually costs to push mass through space at the speeds that interstellar travel demands. The Oort Cloud is where our solar system ends. What lies beyond it, and what it would truly take to get there, is a problem of a completely different and far more brutal kind. 250 astronomical units. That is the target. That is the number that represents the most ambitious deep space mission NASA has formally studied, the proposed Interstellar probe, a concept developed at the Johns Hopkins Applied Physics Laboratory, targeting a launch window between 2036 and 2041, 250 astronomical units in approximately 50 years. A machine built with the best technology available in the coming decade, launched on the most powerful rocket America has ever built, flung outward with a gravitational assist from Jupiter, and still arriving at its destination half a century later at a distance that is 1/8 of the way to the inner Oort Cloud and less than 1/10 of 1% of the way to Alpha Centauri. 250 astronomical units would be genuinely revolutionary. The Voyager probes, at their respective distances, were never designed to study interstellar space. They were built for planetary science and happened to survive long enough to cross the heliopause with aging instruments never intended for that environment. A dedicated probe with modern instruments reaching 250 astronomical units would give us our first real, high-resolution portrait of the heliosphere from the outside, our first detailed measurements of the very local interstellar medium, our first direct sampling of interstellar dust and plasma with 21st century technology. It would answer questions Voyager 1 raised but could not fully resolve. It would be extraordinary, and it would still be nowhere near leaving the solar system in any robust sense of the phrase. But 250 astronomical units is not the number that captures public imagination when people talk about reaching the stars. The proposal that does is Breakthrough Starshot, the most aggressive near-term interstellar concept ever funded by private money, and the one most frequently cited when optimists argue that interstellar travel is closer than we think. Announced in April of 2016 by the late physicist Stephen Hawking and investor Yuri Milner, with initial funding of $100 million. Breakthrough Starshot proposed something so audacious it reads almost like science fiction even now. Rather than trying to accelerate a large spacecraft to interstellar speeds, which is energetically catastrophic as we are about to see, the concept proposed accelerating something almost weightless. Gram-scale wafers, microchips carrying cameras, sensors, and communication equipment, each attached to a sail a few meters wide, made of material thinner than a human cell. These tiny probes, called starchips, would be pushed by a ground-based laser array, delivering 100 gigawatts of power concentrated onto the sail, accelerating each chip to approximately 20% of the speed of light in a matter of minutes. At 20% of light speed, the journey to Proxima Centauri, the nearest individual star, at approximately 4.2 light-years, would take roughly 20 years. The chips would fly through the Proxima system at enormous velocity, with no ability to slow down, capturing data for perhaps a few hours as they pass, then transmitting what they found back to Earth over the following 4.2 years at light speed. From launch to first data return, approximately 24 years, a single human lifetime contains that span. That is not geological time. It is not the 73,000 years Voyager 1 would need at its current speed to cover the same distance. 20% of light speed changes the entire conversation if it can be achieved. The word "if" is doing enormous work in that sentence. In October of 2025, Scientific American reported that Breakthrough Starshot was quietly becoming inactive, burdened by a cascade of unresolved technical problems accumulating faster than solutions could be found. The program had not been officially cancelled as of that reporting, but its forward momentum had stalled significantly. This matters not as a verdict on the people who attempted it, who were serious scientists and engineers working on genuinely hard problems, but as a precise and honest signal about what the physics actually requires. Because each individual problem breakthrough Starshot encountered is not a project management failure. Each one is a window into why interstellar travel at any scale, from any civilization, at any level of technology short of the truly advanced, is a problem of a categorically different kind than anything humanity has previously attempted. Start with the laser array. 100 gigawatts of coherent laser power, delivered to a target just a few meters wide, from a ground installation tracking a sail that will be accelerating away at a significant fraction of light speed within seconds of illumination. For reference, the entire electrical generating capacity of the United States is approximately 1,000 gigawatts. Breakthrough Starshot's laser array would require power equivalent to 10% of America's total electrical output focused into a single beam, fired in a pulse lasting minutes. The engineering of building a laser array that powerful, maintaining phase coherence across thousands of individual emitters, pointing it accurately enough to remain on a sail the area of a bedroom, while the atmosphere distorts the beam, and the target is already moving at thousands of kilometers per second. These are not problems with established partial solutions. They are frontier challenges, each one individually at the absolute boundary of what current physics and materials science permit. Then there is the sail material itself. To survive the acceleration without vaporizing, the sail must reflect the laser energy with extraordinary efficiency, absorbing almost none of it. To achieve the required force-to-mass ratio, it must be thinner and lighter than anything currently manufacturable at scale. To survive the journey through interstellar space, it must withstand a radiation and particle environment that becomes lethal at relativistic speeds. At 20% of light speed, a hydrogen atom sitting stationary in interstellar space hits the sail with the energy of a cosmic ray. The interstellar medium is not empty. Every cubic centimeter contains, on average, approximately 1 hydrogen atom. Across 4 light-years of travel, that adds up to a cumulative particle bombardment that no known material has been demonstrated to survive. A grain of interstellar dust, 1/100th of a millimeter across, impacting at 20% of light speed, releases energy comparable to a small explosive charge. The number of such grains along the route to Proxima Centauri is not small. Current material science has no confident answer for this problem. It has proposals. It has theoretical approaches. It does not have a tested solution. The communication problem is equally fundamental and receives less attention than it deserves. A chip, the mass of a paperclip, traveling at 20% of light speed and receding 4 light-years away, must transmit data back to Earth using a laser powered by what, exactly? The power supply available on a gram-scale chip after acceleration is measured in milliwatts. Pointing a centimeter-scale laser with sufficient precision to illuminate a detector on Earth from 4 light-years of distance, while the chip is still moving at relativistic velocity and the detector is on a rotating planet orbiting a moving star, requires pointing accuracy so extreme that it has no analog in any existing engineering system. Every component of the mission architecture simultaneously touches a frontier with no established solution. This is the new conceptual angle that Part 3 introduces, the one absent from every conversation about the heliopause or the Oort Cloud. Interstellar travel is not primarily a distance problem. It is an energy density problem. And energy density does not yield to cleverness the way navigation problems do. To understand why energy is the actual wall, consider what it physically costs to move mass through space at speeds relevant to interstellar travel. The Tsiolkovsky rocket equation governs every conventional propulsion system ever built. It is not a limitation of imagination. It is a consequence of conservation of momentum. The equation states that to achieve a given velocity, a rocket must carry a mass of propellant that grows exponentially with the target speed relative to the exhaust velocity of the propellant. Chemical rockets achieve exhaust velocities of roughly 3 to 4 kilometers per second. The velocity needed to reach Alpha Centauri in 100 years is approximately 12,000 kilometers per second, or 4% of light speed. The ratio of those numbers is roughly 3,000 to 1. Plug that into the rocket equation, and the required propellant mass for a 1 metric ton payload becomes a number that exceeds the mass of the observable solar system by many orders of magnitude. Chemical rockets cannot approach interstellar speeds. Not slightly, not with optimization. The gap is absolute. Nuclear fission propulsion closes some of that gap by raising exhaust velocities by factors of 2 to 5 compared to chemical rockets, which helps, but not nearly enough. Project Orion, studied seriously in the late 1950s and 1960s at General Atomics, proposed detonating a sequence of nuclear bombs behind a large pusher plate, using the blast pressure to accelerate the spacecraft. The most ambitious Orion designs, using thermonuclear devices rather than fission bombs, projected achievable speeds of perhaps 3 to 5% of light speed for a very large spacecraft. At 4% of light speed, Alpha Centauri is approximately 105 years away. That is within the range of a multi-generational mission, barely. But it requires detonating thousands of thermonuclear weapons in the space near Earth, a proposition that collides with the Partial Nuclear Test Ban Treaty, with every political and legal framework governing weapons of mass destruction, and with the practical question of manufacturing thousands of precisely engineered thermonuclear devices for propulsion rather than deterrence. Project Orion was cancelled in 1963, partly for exactly these reasons, and no successor program has advanced it meaningfully since. Fusion propulsion, using controlled thermonuclear fusion rather than bombs, offers genuinely superior exhaust velocities in principle and avoids the political catastrophe of Orion. A fusion drive achieving exhaust velocities of 5 to 10% of light speed would make interstellar missions physically tractable for robotic probes within timescales of centuries rather than millennia. The problem is that controlled fusion has been the primary unsolved engineering goal of civilization for 70 years. The National Ignition Facility at Lawrence Livermore achieved fusion ignition in December of 2022, producing more energy from a fusion reaction than the laser energy delivered to the target, a genuine milestone. But ignition in a laboratory setting using a building-sized laser to compress a tiny pellet is not the same as sustained fusion energy production, and sustained production is not the same as a compact fusion engine producing directed thrust in space. Each of those steps represents a separate and substantial engineering challenge. Fusion propulsion for interstellar missions is physically sound and developmentally remote, separated from current technology by multiple generations of engineering that have not yet been attempted. Antimatter annihilation sits at the theoretical ceiling of chemical energy density, releasing energy equivalent to full mass energy conversion when matter meets antimatter. 1 gram of antimatter annihilating with 1 gram of matter releases approximately 43 kilotons of energy. A spacecraft powered by matter-antimatter annihilation could reach meaningful fractions of light speed with propellant masses that do not violate the rocket equation catastrophically, The problem is production at scale. The entire global output of antimatter from every particle accelerator on Earth, running continuously and combined, produces approximately 10 nanograms per year. A modest interstellar probe might require hundreds of kilograms of antihydrogen. The gap between current production capacity and mission requirement spans more than 19 orders of magnitude. To put that gap in perspective, if humanity began producing antimatter at current rates and continued without interruption, it would take longer than the current age of the universe to accumulate enough for a single interstellar mission using antimatter propulsion. This is not an engineering gap. It is a statement about the difference between what physics permits and what civilization currently produces. Laser sails, the breakthrough starshot approach, sidestep the rocket equation entirely by leaving the propellant source behind on Earth and pushing the spacecraft with photon pressure. This is genuinely clever and physically legitimate. But the laser array required is itself an energy infrastructure problem of the first order. 100 gigawatts delivered coherently to a moving target is a power level that does not exist in any current or near-term installation on Earth, and building it raises materials, thermal management, and atmospheric compensation challenges that remain unsolved at that scale. The concept identifies the right direction, while the road to that destination has not yet been built. What all of these propulsion concepts share, from nuclear pulse to fusion drive to antimatter to laser sail, is a common requirement: energy at a scale that civilization currently does not produce in usable form for propulsion purposes. This is not a funding problem. Governments and private investors have spent billions on fusion research, on advanced propulsion concepts, on space exploration broadly. The limitation is not financial, it is physical and developmental. The energy densities required for interstellar travel are real and achievable in principle, but achieving them requires a civilization that commands energy, resources, orders of magnitude beyond what any current or projected near-term society controls. The stars are not waiting behind a door that money will open. They are waiting behind a door whose key is a form of power that humanity has not yet learned to generate at the required scale. That distinction between a solvable engineering problem and a civilizational scale transition is the honest foundation from which Part 4 cannot look away. Here is the question that all of those numbers have been building toward, the one that lives underneath the energy calculations and the propulsion concepts and the mission timelines. What does it mean to be a species that understands exactly how far it is from the stars and has no realistic path to reaching them in any foreseeable time? Not a rhetorical question, a genuine one, because the answer is not obvious. And it is not the same as saying we are stuck or we are small or we should feel diminished. It is a question about what kind of thing we actually are right now in this specific moment of civilizational development, and what honest self-knowledge at cosmic scales produces in a mind capable of holding it. Start with what is genuinely new in Part 4 that the previous 3 sections did not address. Parts 1 through 3 established the physical constraints, the heliopause, the Oort cloud, the energy wall, the propulsion gap. All of those are external facts about the universe. Part 4 introduces something different. It introduces the constraint of time as a biological and institutional reality rather than a navigational one. Because the problem of leaving the solar system is not only that the distances are enormous and the energy requirements are vast, it is that the timescales involved are categorically incompatible with the way human civilization currently organizes itself, plans for the future, and sustains commitment across generations. Human institutions do not persist unchanged across centuries. The oldest continuously operating universities are roughly 900 years old. The oldest surviving legal systems have transformed so fundamentally over that span that their founders would recognize almost nothing in their current form. The United States government, one of the more durable modern constitutional structures, has existed for fewer than 250 years. Corporations rarely survive a century without fundamental transformation. Scientific agencies like NASA have existed for fewer than 70 years. And the proposed Interstellar probe, if launched in 2036, would require 50 years simply to reach 250 astronomical units, which is not the Oort Cloud, not Alpha Centauri, not even the beginning of what leaving the solar system truly means. A mission to the outer Oort Cloud at 100,000 astronomical units, traveling at 10 times Voyager 1's speed, would take approximately 2,800 years. A mission to Alpha Centauri at the same speed would take approximately 7,300 years. No institution in human history has maintained unbroken operational continuity across 7,000 years. Not one. The concept does not have an example. This is not a peripheral concern to be solved after the propulsion problem. It is a central constraint of equal importance. You cannot send a mission you cannot sustain. You cannot sustain a mission across timescales that exceed the lifespan of every organizational structure humanity has ever built. Any serious interstellar civilization, one actually capable of mounting and completing a mission to another star, would need to have solved this problem first. It would need institutions, or something that functions like institutions, capable of maintaining purpose, knowledge, funding, and operational continuity across periods that dwarf recorded human history. That is not a technology problem. It is a problem of political philosophy, of cultural continuity, of what it means to make a commitment on behalf of people who do not yet exist and cannot consent to the obligation being placed on them. The communication problem compounds this in a specific way that deserves its own examination. A signal traveling at light speed from a probe at Alpha Centauri takes 4.2 years to reach Earth. A reply takes another 4.2 years to travel back. Any interactive mission management, any real-time adjustment, any responsive science operations, all of it becomes impossible across interstellar distances. The probe must be fully autonomous. It must carry within itself the capacity to make every scientific, navigational, and operational decision it will ever face, without the possibility of consultation, without the ability to ask for help, without any connection to the civilization that built it, beyond the ancient instructions encoded in its systems before departure. This is an artificial intelligence problem of a depth that current systems do not approach. Autonomous navigation in complex and unpredictable environments over decades of travel, autonomous scientific decision-making about which observations matter and how to prioritize limited power and storage, autonomous fault detection and repair across systems that may degrade in ways their designers never anticipated. None of these capabilities exist at the required level in any current or near-term AI architecture. NASA's Perseverance rover demonstrated AI-assisted autonomous driving on Mars in 2025, planning routes and navigating terrain without real-time human input. That is a genuine and meaningful capability. But Perseverance operates in a light delay environment, measured in minutes and on a surface whose basic physics is well understood. An interstellar probe operates in an environment whose properties at the destination are unknown, across a journey whose hazards may include particle impacts, magnetic field variations, and physical phenomena not yet characterized, with communication delays measured in years. The gap between Perseverance's autonomy and the autonomy required for interstellar mission management is as large as the gap between a pocket calculator and a human brain. We have begun. We have not arrived. Now, consider what it means to attempt a crude interstellar mission under these constraints, not as a practical proposal for the near future, which it is not, but as a thought experiment that reveals the depth of the civilizational challenge. Human beings require air, water, food, radiation shielding, psychological stability, meaningful social structure, medical care across the full spectrum of human disease, and some form of purpose sufficient to sustain commitment across what would be, at minimum, decades of travel and more likely generations. The radiation environment of interstellar space, beyond the heliosphere's protection, is not merely uncomfortable. Galactic cosmic rays, high-energy particles, accelerated by supernovae and other violent events in the galaxy, penetrate spacecraft hulls with an intensity that current shielding cannot fully block at practical mass. Long-duration exposure damages DNA, elevates cancer risk, and may progressively impair neurological function in ways that have not been fully characterized even in the lower radiation environment of the International Space Station. NASA has studied this problem intensively in the context of Mars missions, which involve exposure durations of months. A crude interstellar mission involves decades at minimum. No current shielding technology addresses that timeline at mass levels compatible with any conceivable spacecraft. Suspended animation, the elegant solution science fiction has always reached for, has no established biological foundation in humans. Human cells do not tolerate the kind of metabolic arrest that would be required for decades-long suspension without accumulating damage that current medicine cannot repair. Some organisms tolerate extreme states of dormancy, tardigrades being the famous example, but the mechanisms involved are not translatable to complex, multicellular organisms like human beings in any way that current biology understands or any near-term research program is close to solving. Generation ships, the alternative in which crews live full lives aboard a vessel and pass the mission to their children and grandchildren, raise questions that engineering cannot answer. What is the psychological reality of a person born into a closed environment who will die before seeing the destination? What social structures maintain mission integrity across generations that had no voice in the original commitment? What prevents the 100th generation from simply deciding that their ancestors' goals are not their own? These are not hypothetical edge cases. They are the central human problems of the mission, and they live in domains of ethics, psychology, political philosophy, and social theory that have not yet seriously engaged with the interstellar problem because the interstellar problem has not yet required them to. All of this, the institutional timescales, the communication delays, the autonomy requirements, the biological constraints, points toward the same conclusion that honest reflection on interstellar travel always reaches eventually. We are early, not early in the sense of being close to the starting line of a race that is already underway. Early in the sense of being at a stage of civilizational development that is genuinely and substantially prior to the conditions that interstellar travel requires. The civilization that sends the first meaningful mission to another star will not simply be more technologically capable than the present one. It will be different in kind, more patient across generations, more capable of sustaining commitment across timescales that exceed the lifespan of its current institutions, more honest about the difference between what is possible in principle and what is achievable in practice, more integrated in its relationship between artificial and human intelligence, more commanding of energy resources that currently exist only in theoretical proposals. That civilization may grow from this one. The transition from a solar-bound species to an interstellar one may be as gradual, as multi-generational, and as impossible to perceive from within as the transition from hunter-gatherer societies to agricultural ones, a process that unfolded across thousands of years with no single generation aware it was happening. Each small step, each new mission, each refinement in propulsion or materials or autonomous systems or energy production is a contribution to a transformation whose full shape will only be visible in retrospect. From a distance of centuries or millennia, the people who eventually launch the first genuine interstellar probe will not think of themselves as completing something that began in 1977 with Voyager 1, but it will be true nonetheless. What remains for this generation, for the civilization that currently exists, is something more modest and more honest than the dream of the stars. It is the work of understanding. Every measurement IMAP makes of the heliosphere boundary adds to a map that will still be useful thousands of years from now. Every comet tracked back to the Oort Cloud refines our model of the solar system's true extent. Every test of autonomous systems on Mars or the Moon pushes the boundary of what machines can do without human supervision. Every advance in fusion research, however incremental, is a step along a road whose destination is the energy infrastructure that interstellar propulsion eventually requires. None of these steps are wasted. None of them are irrelevant to the interstellar project, even if no individual working on them will live to see that project launched. They are the foundation being laid for a structure whose architects have not yet been born. The Voyager Golden Record understood this intuitively, which is why Carl Sagan and his colleagues chose to include it on a spacecraft whose chances of ever being found were negligible. The record was not a message to aliens. It was a message from one civilization to its own future, a declaration that the species capable of building Voyager 1 was also capable of wondering what it meant to have done so, and of choosing, despite knowing the distances involved, to reach anyway. That reaching, that persistent extension of human presence and human knowledge toward the outer dark, even when the distances make any return impossible and any destination unreachable in any living lifetime, is itself a form of meaning that does not require arrival to be real. We are a solar species. We belong, for now and for any foreseeable human future, to this star, this system, this vast and only partially explored neighborhood of planets and moons and comets and dust and interstellar visitors passing through. The solar system is not a small thing we are on the verge of transcending. It is a world of staggering richness and complexity that we have only begun to understand. The fact that we know its true boundaries, that we can calculate the distance to the Oort Cloud and place Voyager 1 on the scale, and understand precisely why it has not yet left and will not leave in any powered sense for tens of thousands of years, is not a source of frustration. It is a form of genuine knowledge that only a civilization of a certain maturity can produce, and genuine knowledge, honestly held, is always the only real starting point for anything that comes after. The solar system will hold us for a long time yet. and the stars will wait, as they always have, at distances that do not diminish because we name them, in a darkness that does not soften because we understand it. That is the harsh truth about leaving, and it is, in its own way, a truth worth knowing. Rest now, dreamer. The outer dark is patient, and the stars will hold their distance a little longer.